Good evening, everybody. Welcome back to the stream. My name is Dr. Lambda, and tonight we're going to be looking at something that is very close to my heart. We're going to be playing around with programming languages. Specifically, we're going to be playing with a very low-level programming language, looking sort of or feeling like an assembly language. And we're going to be looking at how memory can be manipulated and how we can do some sort of fun stuff by implementing a virtual machine. Now, there are two different things that we tend to call virtual machines. There are the things that sort of simulate running an operating system without running an operating system, like supplying, let's call it virtual hardware and stuff. That's not the type we're going to be doing tonight. We're going to be doing the other interpretation, which is the one of Java's virtual machine, for instance, that takes instructions in a very low-level language and then simulate them as if they were instructions on the actual hardware that you could run. So I guess in some sense it's sort of similar, although the technologies are quite different in feeling and in use. So the reason for having a virtual machine is that you don't need to actually code against the concrete GPUs. Hi there, welcome to the stream. So instead you can just assume that you have this common layer in the virtual machine that you can code against, and then you just need to implement the virtual machines for each of the architectures that you want to be doing. What we're going to be doing is just playing around with something that looks like, or something that's close to assembly language. So it's a programming language. We're going to make an interpreter essentially, or not essentially, we are going to be making an interpreter. So let's just jump straight in and I'll show you sort of the language that we're going to be playing with. So it's one of my favorite languages. I'm just going to make like a notes file here. Maybe that should have been marked down. We'll change it if it's relevant. It should definitely be marked down. Why not do markdown immediately? Then we can have this nice preview and stuff where if we have code and we mix it with text or explanation or stuff like that. So the language we're going to be implementing has only, as you've seen from the title probably, one instruction, a single instruction. It's called subtract. Branch if not 0. So there's an implicit then here. So really this is short for SBNZ. Subtract and branch if not 0. So it's a very simple language. It has only one instruction, the SBNZ. I just wrote it. And then this single instruction constitutes the whole language. Thanks, Darrell. I thought it would be fun too. So this instruction takes 4 arguments to make this work. It takes A, B, C, and D, but they are different. Hi, Chameleon. Welcome back to the stream. The first 3 are the numbers to subtract and where to store them. So this instruction will execute B minus A and then put that in C, right? So in traditional programming, it would look like this. Hi, little Leia, welcome to the stream. First thought as I saw this, Code War. Yeah, exactly. Yeah, and I made it for Code War. We played around with it. Okay, yeah, so we'll, not Code War, Core War. I don't know what Core War is then. We did something in university with Code War, where we actually implemented things like this. Yeah, so that instruction, and then we do an if, to say if the C is 0, then we jump to, what's a good jump operator? Jump, yeah, jump to the D location, right? So that's sort of what it means, or at least that's our first model of how this instruction is interpreted. Is interpreted as subtract B from A, put it at the location C if C is 0. So we're putting, so C in this case is actually a location in the heap. So we can't just say C here, right? We need to actually read what is at the location C. Similarly, we can't just, we would also like the indirection on these variables. So in fact, we're going to be passing references to cells that have the value that we want to be subtracted. So when I do brackets around something, it means the address of B and the address of A. Or that A, or actually it means the opposite. It means that B is an address, we read what is on that address. We could also be doing that with sort of like the ampersands, if this was a C-like language, I guess. What did you post here? Core Wars. What is it? Programming game. Oh, that looks crazy. Okay, not very zoomed in. Warriors. 2 more battle programs. Control a virtual computer. Yeah, that sounds very similar. That is something that I would also be doing with this if we could still, for instance, go to places and meet up and play with programming or just talk to each other. Yeah, so in fact, all of these things up here are really addresses, or I mean, the first 3 are addresses, and the 4th is the actual number, the destination. So because we have an architecture with a single instruction, a program in this language would sort of look like, it could say SBNZ. If we wanted to subtract like 5 from some value, let's say 10, and then store that at like a location, let's call it, well, yeah, we will want to store this at a location, so that could be like 10. And then go to the next instruction, and then over here we can say subtract 0 from 1 in both cases, and then store that somewhere else. No, go to whatever, -1. So in our convention here, we're going to be assuming that if you go to a negative address, you mean the program to stop, right? Because, yeah. So in this case, this pattern of subtracting 0 from 1 and then storing that somewhere, that could also be like, oh yeah, so yeah. So this is sort of a trick, right? Because we're doing the, if we translate this instruction, that's what I'm trying to say, we will do 1 minus 0, and then we will put that at the address where 1 is, right? So in the place where 1 already is, we'll store this value. Well, this value is 1, 2 already, so this will have no effect, but it will always check afterwards what is whatever is on the value of 1. Well, that's a 1, right? And so if it's not 0, oops, I forgot the not. That sort of changes everything. Then we'll be jumping to -1, right? So that's sort of what that means. Yeah. And this is always true, right? 1 is never 0. So we always jump. So the last thing here, this one, sort of simulates how to do a jump. Copied itself, then increased its program counter. Hey Jens, welcome back to the stream. Yeah, so this pattern is like a jump, and we can think of it like a jump to -1 in this case. And this one will subtract the 5 from 10 and then store that at location 10 in the memory, which is actually fine. And then no matter whether that's, whenever we have a 4 here, the location will be sort of, or maybe we should talk about that now. Because we only have one instruction in our architecture, there's no actual need to write it down, right? Because we know that every 4 numbers, we should just put a new instruction, or there should be an SBNZ instruction. So here, we just have 8 numbers, so we know that's going to be 2 calls of the SBNZ instruction. And so in that way, we should write up the fact that this is jump. Compiling, or whatever we call it. We'll have this pattern to D is equal to a jump to D. So now, because we don't need to write down the instruction, these numbers just specify where to go to in the memory, right? So 4 would be the execute from an instruction on the 4th thing. So in this case, no matter what the result is, if this is 0, then we go to the next instruction, so we just add 4 and we start at 0. But if it's not 0, then we go to 4. So in both cases we go to 4, right? So that's how we're going to be doing the not branching when we don't want to. We're just going to be branching to the same place that we would be going anyway. That is our location plus 4. Competing programs do other things, like continuously write an invalid instruction. So if the operation is a single instruction, the hope is that it will try to execute that instead of copy operation. That sounds difficult, but it may be because I've never heard of anything like that before. I don't even know how to wrap my head around something like that. Yeah, so we've already discovered the jump location. The jump instruction can be sort of simulated with this thing. So what else? Oh, I shouldn't have deleted this. So in this example here, we have these brackets. So the brackets are not a program written in SBNZ. It's actually just a string of numbers. We can't have brackets in that. That doesn't make any sense, right? It doesn't understand what brackets are. But we understand what we mean by the brackets. We mean at location, the place where 10 is stored, or the place where 5 is stored. So in fact, using 10 here is sort of inefficient, because that means we're going to have a value down here somewhere that we don't know what is. And then this one is going to be number 10, where we're going to put the result of 10 minus 5, right? Because we said that's going to be at cell number 10. And so for cells that I know are going to be overwritten, I like to just put 4 9s. That's very easily spottable by the human eye and be like, okay, we're going to write to that location at some point. But we could just write any value, it doesn't really matter. You can also just put -1s or whatever. We also need, if we're going to have to use these numbers, then we need them to be in memory, right? Because we can only use addresses. So every time we have something that has brackets around it, we should put it somewhere in our store or heap or whatever we want to call it. So here I've just put the 4 numbers that we're using, the 4 constants. So now we can say, well, 5 is actually location number 11, right? Because if we count the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. We need another one. So actually, if we have 2, it might make sense to just bump up the 0 and 1 to these positions. So now 5 is at position 11, 10 is at position 12 in the heap. We'll write to position 10, that's this one. We'll jump to 4, that's here. 0 is at position 8, 1 is at position 9, and 1 is at position 9. So this is the program that we had. That is now gone. But that's the same thing that it's doing, right? This is, I should have just copied it so we could have preserved it. SBNZ 5 from 10, not commas. Store it at location 10, go to 4, SBNZ, location, subtract 0 from 1, store it at 1, and go to -1. So this, the program above there, is what's translated into this string of numbers down here, right? Let's move that up because it has nothing to do with the compiling. It's just explaining the language. So we have it here. Yeah. So this thing here translates into a string of numbers. And this is actually a valid SBNZ program that subtracts 5 from 10 and then ends the program. So that's cool. That's super nice. What else do we need to discuss? Do we need anything else, or can we just start programming then? I think we can just start doing it. Let's implement something that can take a program like this and then execute it. And we're gonna need to determine the language. What do you want, guys? Are we gonna do TypeScript or Java today? Or let's stick with those two. Yeah, sure, let's stick with one of those. TypeScript, we go for TypeScript. Cool. Let's call it SBNZ. Don't open over there. Whoa, I didn't even know I could. Okay. Okay, so the first thing we need is a lot of things then. We need to initialize the TypeScript. Hello. Initialize the TypeScript. Emacs Lisp, fight me. I don't want to fight you, Jens, but we're not doing that. npm init -y. Oh, that's not how, yeah, that's not how that one works. What else do we need? We need we don't, well, I mean, we might as well do git. Why not do git immediately? Okay, we are gonna need very quickly, well, we can just, let's just simulate right now that we have the program loaded into memory. But we need to also do that through a file. Oh, I have the program over here. I'll copy it. Right, that should have had commas. Well, okay, we can do something easier then by just splitting it here. So now we have the program. We should also discuss what the output is. After executing this program, the output should be well, the same numbers, right? We dump the memory, but instead of 99999, there should be a 5 here. And that's actually the only change I expect there to be, because the only place where we actually write something is at this location. We also write something here, but that's not observable as we've discussed. So this should be the output. Just so we're on the same page. Okay, so we're gonna need a program counter, which is gonna be the index that we're looking at currently. And then we're gonna be like saying while the program counter is greater than or equal to 0. Then we should do the following. We need to get the 4 components, that makes sense. Let A equals program at position PC plus 0. Here, then we have plus 1, 2, and 3. B, C, and D. And as I specified over here, the way we interpret it is by saying, well, whatever is on position C should be overwritten by whatever is on position B minus whatever is on position A here. Yeah, okay, they're numbers. Well, yeah, okay, whatever. We'll make them numbers in a second. If whatever's at this location now is not 0, then our program counter should be set to D. Otherwise, our program counter should just increase by 4. And then it's being a little picky because none of them are numbers, but they are now. What's up? Oh, well, okay, we need to do it up here. Map x plus x. And then we don't need these things. Okay, so that's actually the interpreter for the language, I think. Let's try to run it. tsc-watch. Let's get a new one going. Node SBNZ. Yeah, cool. So it terminated. We might also want to actually look at the result down here. And there we have it, formatted so that it breaks it not quite where we want it, but I think we can cope. 8, 9, yeah, 9 minus 1, 0, 1, 1, 5, 10. Yeah, so that gives actually the output that we expected, which is very nice. Okay, let us then read this from a file instead. File.sbnz. No. Here, take this thing, plop it in there. This is now an SBNZ program. Just a string of numbers. And then we need to say import fs from fs, or is it import star as fs? I think it is. And then we need to install, is it Node.js? No, that's not it. It's types node. Does that resolve this one? It did, nice. Then we also need a gitignore because we have node modules. Here, gone. Okay, our fs then would be the process.argb, and the args would be node, then the name, and then the thing. So it will be 2. This is the file name. Let file name. Here. Then we say fs.read synchronous file synchronous. Wait, do we need the read file? I guess it won't hurt. On the file name, this is the content. And then we can actually just do the same thing we did here. And then it's not content anymore, it's actually the program. Like that. Yeah, and then it's complaining because this is a buffer and not a string. There are easy ways around that. We can just say .toString. There, that will be fine. And now this should do the same thing that it did before, except it's complaining that we didn't give it a file, which is fair. And now it did give the same thing, 5.5. So that also works. And then we should also output the result to a file, I guess. fs.writeFile sync here to file name, and then we're just gonna append out to it with the program here, .join with spaces. like that. And so when run now, we'll get the out over here and it will have our result in it. Nice. I'm also gonna want, what am I gonna want here? I was totally thinking something. Oh, I'm gonna want to ignore the out files, because they're just outputs. And now they're also highlighted a little bit. They're very easy to see over here. And I can flip back and forth and see easily what the difference is. Cool, 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 cool. We already have the virtual machine now. This is actually a complete language, the single instruction thing. And what we're gonna do now is just play around with that to verify to ourselves that this is actually a complete and very reasonable language that we implemented in, what, 10, 20 minutes? My mom says, hi your mom. Say hi back. Okay, so we are going to be implementing something. Let me just look up something that's interesting. So I have this here file, whoops, of some exercises that we're gonna be doing. Boom. Let's make it fit on the screen. Whoop. We don't need this one. I think we all can remember the rules. Otherwise, we'll explain them again. So let's do exercise 1.SBNZ. So we have a program that we need to finish. So in this implementation here, they're just storing what's it called? They're just using 124 to be the end of program instruction. We're going to be doing -1. And in that sense, 123 is actually the last cell in this implementation, but we're going to have an expanding thing, or a dynamic size. So actually this will be a good test case for our thing, because we need to implement the fact that it should be dynamic in size. So the exercise is to finish the program, and that's because it has the instructions, which we know we don't need. It also has the brackets, which we also know we don't need. So instead, we're going to put the numbers that we have in our program. So 0 is going to be 8, 1 is going to be 9, this one is going to be 9. We have the 5 up here, let's put that, and the 42. And if 1 is 9, then this would be 10, and this would be 11. Get rid of the new lines, and that should be that. Let's try and implement or execute the exercise here. Did it work? I mean, it didn't put anything at location 123, which is a problem. So what we need to do here is check whether C is actually larger while C is greater than or equal to our program length. Then we need to append to our program something. Let's just put 0 in memory. That makes sense, I think. So now when we execute it, it should actually give us a much bigger output over here. And it did a lot of zeros, and at the final position, it has subtracted 5 from 42, as we expected. So that is good. I consider this exercise good. Done. Let's do the next one. Exercise 2. SBNZ. Finish this program. That's very similar to what we did last time. First of all, we know we don't need the instructions, so we can get rid of those. We also know we can't have the brackets, so let's do 0 and 1, like we did before. But in this case, they're not just 8 and 9. They're actually going to be 4, 8, 12, 16, 20. So 0 is 20, and 1 is 21. yeah, like this, and we can just replace all of those. And then we have 5 is the only thing we actually have. So now we put that here, that's position 22, and that's fine. So we do this. Now, the exciting thing is, we have actually written to the place where 5 is now. And so here, this 5, if we just put 22, then that's actually pointing to something that is now the content of 21, which is 1. So it's 5 minus 1 at this place. So we can, of course, just put this. And what we then expect to get as the output from this, I guess actually, let's say you should split space NES, so we can have new lines also in our files. That might make it a little easier to read. So in this case, we actually expected to subtract 1 from 5, so that will store 4. Then subtract 1 from what is now 4, store 3. Subtract 1 from what is now 3 and store it here. So we expect that to give us a 2. So let's look at how it handles this. Out. Yep. So in the position, why does it say 124? Minus 1. Wait, why did it stop at all? Okay, so we have all of these instructions that we had before. We have minus 1, then we have, so we can use the minus 1 as sort of the place to look for when we see where did our program end, right? It ended at minus 1. Then we have 0, then 0 again, then 1, and then minus 20. That feels wrong. We should have 0, 1, and then 2, I would expect, actually. Let's just look at this program. What are these zeros doing? That does not seem right. Did it put in zeros because we have an empty thing when we say split? I think it would have. So that doesn't work. That doesn't work at all. We can, of course, just say we filter where x has a value. I'm guessing that would work. It's taking longer to run, which is bad. It's because it should be not empty. 0 will still look as something that's empty. Still taking a long time, so this also doesn't work. Okay, let's go back to the space. And then not do the line breaks, I guess. Then we need to break this thing here. Hi Blue Spite, welcome to the stream. Single instruction, what does that mean? So it means that we have a language here that looks like an assembly language, like this, but it has only one instruction. Instead of having like push and pop and add and sub, it only has subtract and branch if not 0. And then we can actually build up we can build up all functionality from this single instruction. And currently we've implemented the virtual machine. Virtual machine just means an interpreter for a very low level language. And it's only like this code, 22 lines. Hi Vigo, welcome to the stream. Happy to see you. Yeah, so this is the interpreter, right? It has a program counter and then we can manipulate things. What makes this instruction special is the fact that it works on instructions of things and addresses, or not instructions of things. It works on addresses, and that means we can take something and write to it even, like we can take something that's on the address of 1 and on the address of 5. So we can do very sophisticated stuff, and that's what we're playing around with right now. And I'm hoping it overrides this program with something different. and not loops, but it seems to be looping. Oh, what happened tonight? What do you mean? Oh, what's happening tonight? We're doing a single instruction architecture VM. Unrelated. I really like programming ARM assembly in the 90s with its ability to have conditional branching on every instruction. That seems sort of like what this one can do. Why is it looping? That seems really weird to me. The program counter should reach -1, right? Because we have the -1 here. 4, 8, 12, and then that one would be -1, so that should be fine. 0, 1, and 5. And it's not trying to write to an instruction that isn't in the thing, so I guess we'll have to look at why it's actually looping. It loops 16 and then it goes back to 0. But why is this one? Did I count wrong? Is it not 21? If we have for 16 plus is 20, right? Why did I write 21? Oh, it is 21. This is the 20th instruction. 0 minus 1, stored at 1, go to -1. Yeah, that seems right. 0 minus, go to 12. They're not 20s. They are, oh my god, we're gonna start over on this program because I've messed it up completely. We know that because we have one instruction, we don't need to write it. We can just assume that that's the instruction that we want to run. No, not branching, conditional execution instead of jumping. Oh, okay, interesting. So we could skip an instruction. So because this is 12, the next position here would be 16, 17, and the 5 then at 18. This one should be -1 because that's the way we implemented it. So in fact, this is not 20, this is 16. And these are 17. These are also 17. And these are 18. And these are 18. Good. Serialize the program here so that it works. And then we can run it. And it just, yeah, we don't need to output anymore the locations here. We should probably also do something about the fact that what if we try to read something that is not there? I guess down here. Let's not deal with that yet, but we'll deal with it if it's a problem. It was easy enough to program at the time as I could just intermingle it with basic code. Interesting. So what did we expect this program to go? Oh yeah, we expected the 5 to go to be a 2, yeah, as we discussed, because it subtracts 1 from 5 and stores it at the location where 5 was. Subtract 1 from what is now 4 to get 3, subtract 1 from now what is 3 to get 2, and then finish the program, or yeah, terminate the thing here. So that is actually what we expected. So this program is working. And we can go to the next exercise. Let's go exercise 3, .espens. Okay, in the previous exercise, we had one cell where the 5 was, and that worked as a variable. And that's sort of, that's also how sort of I was thinking about this. We subtracted from the same cell over and over again. So really that works as a variable would, right? And we can just keep writing to that variable. So now we have this one, this program, finish this program. Let's see what it is. So the first thing we know is that this one should be -1. This is just a high cell number, so that's fine. Oh, this one has a letter in it. Interesting. We also know that we don't need to put the actual instruction because we have only one, so it's assumed that that's the one we want to execute. At this point, we need 0 and 1. We almost always will start by having 0 and 1 because of the way we terminate the program. Is branching like jump? Yeah, branching is exactly like jump. So we actually have the fact that 0, 1, 1, minus 1, or 0, 1, 1, this is just a jump. And then this is the location we want to set the program counter to. So this is how a jump would look. Well spotted. So we have 0 now at position, well, I guess 20, this is 20, so this would be 24. So we can put 24 everywhere we have 0. The 1 would then be at 25. I'm assuming and hoping. And then we have A. And we can't really have an A in our program here. So we can just put A for now and then write in that that's going to be, or I guess we have the 5 also. Let's do the 5 first. So 25 was 1, then this is 26. So that's where the 5 is. And the A now would be at 27. So let's just put in that. 27 here. And also here. But we can't have an A in our program. That would crash it, right, when we try to parse it as an integer. So we need to actually initialize this with some value. What I can see in this program over here is that it's going to subtract 0 from 5 and put that into A. So I'm fairly certain this line is the initialization of the variable A. So I guess we should just put a 0 for now, and that should work fine. I kind of want it to work with the new line thing, so we're just going to fix so I don't have to make it into a single line every time. That's going to be a little frustrating. So let's output the program. Let's do -s was the thing that didn't work. S plus, is that it? Let's do 3. So how did it look? Are we still outputting? We're not. Why is that outputting the location? I thought I got rid of that. Oh, it's not. It's just me who scrolled past it. So this is the program that it read. Does it have the extra? No, it doesn't have the extra zeros. This actually looks exactly like the program we would like. Let's see how the output looks. Messed up. Looking at this one over here, what we expect is to set A to 5, then subtract 1 from it 3 times. So I would expect there to be a 2 at location where A was. And then we subtract, oh, and then we write that to the very last cell in our thing. Yeah, so that's a 2. Right, because we duplicate the value that's now in A by subtracting 0 from it and writing it to a very large number. So also we'll see the same 2 up here. Yeah, so it's just, so this one is actually copying from one cell to another. I guess we can put that in our markdown file. Over here. So compiling, what's the usual assembly instruction for copying? I actually don't know. 0 from A to B. We'll like copy from A to B. Something like that. Copy the content of A to the cell B. It's actually just doing a B equals A, right? That's what it's doing. Okay. Good, let's just make a divider here. That was program exercise 3. Let's do another one. Exercise 4. Didn't hit the dot. Here. Because the program is just numbers and the data is just numbers, we can actually have the program modify itself. This is when it starts to get crazy. Here, hashtag A means the cell A. So let's see. I don't want the hint yet. Can you still read this? Yeah, it seems fine. Let me know if this over here is too small for you guys, then I'll increase it. So let's look at this. So we know that we never need to write the instruction, right? That's just there to help us think about it. We can now, and we know that 124 is what we call very readable. Good, that's good. Is -1. So now we need the 0 and the 1 like we always do. And this is cell 0, 4, 8, 12. You guys, if you can please check my math anytime I say a number, just make sure that I actually counted it right. 0, 4, 8, 12, I think that's good. We also need a 5, and we need a 1023 here. So the 5 is at location 14, and this is at location 15. Then we have an A here. What it says is that this one should be this number. Oh, okay. So this number is whatever this location is at. So that would be 0, 1, 2, 3, 4, 5, 6. So this is actually 6. And then whatever's on here, we don't know what that should be, right? So we'll just put 999, just so that it catches the eye when we look at it. So now if we don't need the output anymore up here, this one can go. So now when we run this, I guess actually it would be convenient to also log the, no, one, it's fine. No, it's fine. Let's run it and see what we get. So what do we expect to get before we look at the output? You should always know what you expect when you run code, because otherwise, I mean, you're just closing your eyes and seeing what happens. So in this case, we expected to put, it's easier to read it over here, subtract 0 from 123. So this pattern we already know to be copying the value from this cell, from this cell to this cell. And because there are brackets around, what we're actually going to be moving is the 123. So this will write 123 down here. So it will actually look very much like this line, where we have 123 here. Then we'll subtract 0 from 5 and put that at the location that we just input, like 123. So what I expect this program to do is give a lot of zeros like the other ones, and at the very last cell, it should have a 5. And then it terminates the program. This should be starting to be familiar. We're going to be ending every program with it, I think. At least we have so far. And it's the way to terminate it. Yeah, so I expect it to be a very long list of zeros with a 5 at the end. Let's look. We have a lot of zeros. And at the end we have 5. And I'm fairly confident that if we counted these, there would be 1,023 numbers before the 5. Good. Cool. So this is actually a very interesting thing, right? That the program can actually change the numbers that are program numbers, right? That means we can do some crazy stuff, and I'm hoping it gets even more crazy. How's it looking down here? Is the hint just the solution then? Using the 9s like I do here. Yeah, I mean, okay. That's pretty much exactly what we did. Good. Okay, let's look. Try putting other numbers instead of 99999. What changes? Well, we just put the 999 because we didn't know what to put there. We could actually put anything, right? 1, 2, 3, 4, nothing would change because this value is being overwritten by the first instruction, so it can never change anything. I don't think we need to answer more for that one. Translate this into SBNZ. Okay, so we need a new program. Yeah, okay. Exercise 5. SBNZ. Okay, so this is starting to look more like code that we recognize, or like I mean, I don't know if you recognize this. This looks a little bit more high level. Luckily, the exercise is nice enough to annotate sort of the instruction count or the labels here, which is nice. So it has the go to. It's though it is weird that it has both jump and go to. But I guess that's fine. So let's try to translate this into SBNZ first with the instructions. SBNZ, well, if A is not equal to 0, go to 8. So that we know how to translate, because a branch is just subtracting 0 from a number. So that would be 0 from the cell where A is in, and store it at the cell where A is in, right? That just doesn't so A minus 0 stored at the same location, that's the same. If it's not 0, then go to 8, so we can just put 8 there. And then we have the jump end. I guess this just means stop the program. We also know how that one looks because we've seen it 100 times by now. That's just the 0, 1, 1 pattern, and then -1. So that's jump to end. And then we have subtract the negative of something. So SBNZ, so this is going to be minus B, and then this will be R, and this will be R, and this will be the next instruction, right? We always need to go to it. And so if this is 0, 4, 8, what? 0, 4, 8, 12 will be the next one. It also says it right here, so we got some help there. Then SBNZ would be, whoops, would be this 1 minus the A here, and then go to the next location, which would be 16. And then SBNZ here would be jump to 0. And we know how jump looks because that's what this is. But instead of -1, we jump to 0 in this case. So I think I translated that correctly to the same format that we're used to working with from up here. So let's delete this code. I guess the PDF isn't publicly available. I don't know, I think I can make it publicly available. Where do I share PDFs? Is there like a paste bin? Can you put files in paste bin? Google, paste bin, share file, share PDF, link. Share PDF versions of files, share PDF via a link, boom. I don't think there's anything secret in it. How to share PDFs. What? Share files online, tiny URL? Is that not a thing? Tiny URL, shorten URL, that's not what I wanted. Paste bin. Can anyone, thank you Jens. No, not, what? I expected that was like a place to share a file, upload a file. What is this? Can I just put a file somewhere? If someone can tell me somewhere I can actually just upload the PDF and give you a link, then you can have the PDF. It also starts with a nice introduction to the whole thing, like what SBNZ is. So if you didn't catch the start, it's right in there. Okay, yeah, so I think this is a faithful translation. And so now the exercise is just to translate this into actual SBNZ. And as we've done before, we start by eliminating that one. You just send a post request with a file and voila, it's online. To where? Where do I send the file? Like, if I want to share a file with you guys, where do I put it? Was the question. PDF host? What's this thing? Docdroid. Upload and share PDFs. That does sound like what I want. Added, updating, protected by capture, okay. Uploading. It's not going insanely quick. View, share. No. Oh, the link is right here. Maybe this link works. Let me know, guys. If that works, and then we're just gonna continue. So we need the 0 and the 1 like we always do, and these are at location, well, 0, 4, 8, 12, 16, 20. I think this is 20, and then this would be 21. Worked, thanks, you're welcome. 21, 21, 20, 21. Okay, so we have all of those done. We also have an A, I can see. We have a minus B, and we have an R. Okay, so if this is 21, then A would be 22 in everywhere. And then minus B would be 23, and R would be 24. Good. And so what does it say? Having the variables, yeah, we do. What is the result if A is 3 and minus B is minus 4? So that means we put 3 and 4, and I guess R is just 0. Yes, it didn't tell us what R should be, so let's just put 0. It definitely has to be something, right? Yeah, because it's not initialized anywhere, so it has to be something. Okay, let's run program 5 and see what we get. Oh, we should try to figure it out before we run. So what it's doing is it's saying if A is not 0, go to 8. So it skips the done thing. It sets R to R minus B. Okay, so it actually adds B to R and then subtracts 1 from A and then jumps to 0. And so it's, okay, so it's actually adding B to R A times, right? Horrible net today, I'm 30 seconds behind, and the Twitch video stat says I have minus frames per second. That's a fairly bad frame rate. That definitely is. So I think this is actually multiplication, right? Because it has the loop structure and it keeps adding B to R. So I think it's A times B. So in this case, it would be 4 times 3 would be like 12, I think. You can check my math on that. So what I expect is that this program outputs 12 in this location once it's done. Let's see. Yeah, and it has 12 in the last position. Good. So I think I'm right on that. Yeah. 0, 1, 1, 0, yeah. And this was the A and this was the minus B. Good, cool. So it's saying it's a bit weird that our variable is minus B and not just B. Add a line to the beginning of the program of the last exercise so that B is equal to 0 minus B. Yeah, that makes sense, right? So our B is this variable, and instead of having 4, we should just have 4 here. So it's 3 times 4 equals 12. So we can do that by just saying, take this variable here, that is B, and I guess that was at location 20, 21, 22, 23. So take 23 and subtract that from 0, which was 20, and then store that at location 23 and go to the next instruction. So the problem we have now, which I hope some of you spotted, is the fact that we've actually added something now to this program, and we've already hard-coded that this 0 is at position 20, but having added 4, it's now at position 24. So all of the numbers now need to increase by 4 except -1. And no, all of the other numbers. So this will be 4, this would be 26, 26. This then will be 12. This will be 24, 25, 25 minus 1 stays the same, 27, 28, 28, and 16. Then we have 25, 26, 26, and 20. Finally, we have 24, 25, 25, and 4. These numbers down here stay the same because they are our constants. So I hope we did that correctly, but there's only one way to find out. So now we have 3 by 4 is 12. So I expected to still have 12 there now. It did not. It's looping. Cool. Why is it looping though? It goes here. It says if 27. Which number is wrong? 4, yeah. 8, 16. That's bad. That's quite bad. 4, 12. This is 8. This is 12. This is 16. No, that's good. 20, 24, 25, 6, 7, and 8. Okay. No, that looks fine. 24. Oh, these are wrong. These are not 23 anymore. This is actually 27. 7 and 24. And then it terminated immediately, so maybe that's right. Let's look. And it has the 12. It also put the -4. So the first line flips the sign of this one, so that's fine. But it did correctly calculate that 3 by 4 is 12. Let's give it a hard one. Let's do 7 by 11. I mean, it's hard, but I can do it still in my head. Let's look what it gets. It's quick. It's 77. That's correct, guys. I even checked it myself. Cool. So we have a multiplier written entirely in just, here's the memory dump. Figure it out, right? I think that's cool. Exercise, what are we up to? 6? Let's see. Translate this into SBNZ. Let's look at this code here. Okay, so there are fewer labels this time to sort of navigate by. It's obvious that it starts with 0. I think it's only there because there's a jump to 0. And, okay, and 8 also. Okay, so let's see how to translate this. Well, if A is not 0, then go to 8. We already know how to do that. SBNZ, take whatever's on location. Take 0 and subtract that from A, store it at A, and then go to the jump that we have. Jump end we also know how to do because it's 0, 1, 1, and then -1. That's this one. So now at 8 we have R equals B. Insert the code for multiplying, so we did figure that out correctly. I mean, we can't just insert this code, right? Because the numbers won't match up at all. So that's a little unfortunate. Do we need to actually translate it again? We might actually need to. Okay. SBNZ with, what would that be then? We start by subtracting something from, so B from 0, and storing that at location where B is, and going to the next one. So if this is 8, this is 12. At the 12 we say, if it's not 0, we know that pattern, it's this thing. It's actually the A that we're checking on here. Go to the next thing, so it won't be 16, it'll be 20, because then 16 would also be the end. Oh, but the end here might be something different. We might need to change this one. I think we will. Then we have this line where we subtract minus b from a, which in this case will just be b from r. And this is now up to, if this line is 20, then the next one is 24. Then we have a equals a minus 1. That's also pretty easy to do. We have the a, and then the 1. And then go to the next one, which is 28. And then jump to 0. But instead of jumping to 0, a jump that just looks like this. Instead of jumping to 0, we need to jump to where the multiplication code started, which would be here, 12 actually. Yeah, and that means if this is 28, this is 32. So the end of the multiplication code is actually 32. Okay, so now we have this. In our location R, we have the multiplication. I think this should be an A, right? Right? No, it shouldn't be an A. So it's now, oh, that should be the, what should that be? The R is something. And we multiply it by B. Okay. And then we say A minus 1. So we have different A's in play here. That might be confusing. I don't know how to. Okay. Yeah, so there's something here. We have different variables in place, right? For R and B. R and B, funny. So I guess instead of using these, we should say the A is actually R. The R from before will just give a new name, like R prime here, and then have the A be an R. Yeah. So this A would be R. This would be R. And then after we're done, we have moved the program from, so it will have something like 3, 4, 12. We actually need to, after it's run, this will be 0, this will be minus 4, and this will be 12. So we need to move this 12 into this variable here for it to work. So we subtract 0 from whatever's on the R and move it into the A, and that's the R prime, and that's the R. Yes. And then we need to subtract 1 from the actual A according to the program over here. Oh, we need to update these. So this is 32. This is 36, and this is 40. And then jump to 0. Okay, at least that one is pretty easy. It's 0, 1, 1. I think that's correct. What do you guys think? Did I hit it? Did we not hit it? Could someone just check that all of these line up correctly? Okay, so to translate this, best fail. Funny. Okay, so we're first gonna need to get rid of these. Then we'll take, then we'll take the 0 and 1. If this is location 40, this is 44. So we can just replace bracket 0 with 44. That means we can replace bracket 1 with 45. Then what else do we have? We have an A, B, an R, and an R prime. So the A would be 46. The B would be 47. The R would be 48. And the R prime would be 49. And then we need to initialize these to some reasonable values. It gives us two of them. A should be 3, B should be 2. R should be at least 1, right? Because we're multiplying with it, so it doesn't make sense to have it be 0. But this one can be 0, I think. Okay. So, due to the fact that we insert multiplication in the middle of this, and it has a loop where it keeps multiplying, I'm fairly convinced that this one will be the exponentiation, which means in this case it should give us 9, right? 3 to the power of 2. No, because the A is actually the one that's counting down, so actually it's 2 to the power of 3. So this should give us 8, I am expecting, if we did everything correctly. Let's see what it gives. It's fast, good. And where does it store its result? This does not look good though. I feel like 0, 0, 1, 0 minus 2, 0. So we are subtracting R needs to be 1 multiplied by B. So B stays the same, right? Well, it gets negated, but that should be fine. Oh, that's not fine. That's not fine at all, because we keep negating it. Okay, yeah, that's a problem. So where do we negate? Well, does it matter? What was the output? It was minus 2, which is the negative B, so that makes sense. That that A is 0 also makes sense because we keep subtracting until it's 0. But that this R is 0 is alarming. Why did that one get to 0 when it started at 1? So this one is 49, so this is 48. Time to read all of these now. This is not the most readable language, I will admit that readily. If R is 0, then move from that one into that one, that's good. Subtract B from this thing repeatedly. And subtract B from this one, subtract 1 from the R. That's all fine, put that in there. So what's weird is that this one is really low. Whereas it should have been not very low. We should also set it to 0 somewhere, which we're also not doing. Which is bad. Huh. Indeed. So this R keeps being subtracted. Put in here B, then set it over here. Then put it over here, then set it over here. Each time we move it. I think that should be fine. I don't understand why this is wrong. When we put the 0 into this one. A minus 1, but A here is, no, that's the actual A. This A is R, and this R is R prime. That means this should check on the R prime. No, the R. This is the R, 48. And it does check on the 48. Is this one the thing that's negating it? It is. So what line is this? 8? Yeah, so we don't want this to be line number 8, because we only want to negate B once, in fact. So this means go to 4, then this means go to 12. 0, 4, 8, 12. So the rest, 16, 20. Yeah, the rest is good. Go to 32, where we set that one over there. This still shouldn't have changed much. Yeah, it's still 0 here, which is weird. 0, 1, 0, 2. Why is this 2? That should be negative 2. Is it not 47? 0, 4, 8, 12, 16, 20, 24, 30, 28, 32, 36, 40, 44, 45, 46, 47. Subtract 47 from 44, store that at 47. Why then is this not a negative number? We never touch B otherwise, right? Yeah, we never touch B. That is mysterious. It is 6, right? I'm looking at the right thing. Am I off by 1 somehow? This is 44, 5, 6, 7. I am totally not spotting why this one is not being negated. It even has it right here. 44. Subtract this number from, subtract this number from 44, which is 0. 4, 5, 6, 7, minus 2. This is confusing me completely, why this line isn't flipping that one. Do we have like a tailing space somewhere or something? No. Okay. Could it terminate without doing it? No. Could it do it multiple times? Yes, it could. This is minus 2. Good. And this is 6, which is very close to correct. Right? It should give 8. It's only off by 2. So I think that's pretty solid. So, okay. So it's not giving the 6, so we translated something wrong. Which of these numbers is wrong, guys? Help me spot it. This is minus 2. We're not resetting this to 0 after copying it. That might actually be the issue. Would it though be the issue? No, that would actually make it too large, I expect. So where do we copy this one? We copy 44 48 to 40, 49 to 48 here, and that means that at the very next location here, we can put 0. We can put 0, which is 44, into 49, and then go to the next one. So now all of them have to be incremented. Great. 44. This is still 4. So that puts a 0 into that one. And now we put an extra instruction. So they all need to increment by 4. 51, 48, 51, 51 here. Maybe not do it like that. Maybe do it in the order they appear, because otherwise I'm gonna mess this up. 50, 50, 12 stays the same, 48, 45 becomes 49. This becomes 52, 52, 48, 48, 49. So, did you guys have a good day? Did you write any programming today? Write any programming? Did you do any programming? 353, 53, 52, 52, 49, 48, 49, 49, 49, 53, 48, 48, 48, 53, 50, 50, 49, 48, 49, 49. Boom! Easy. Let's see if it runs. It does not run. Oh no. Oh no, oh no. Where do we go so wrong? That should still hold. This is all fine. 46, 44, 48, 49, 50, 51, 52, 53. So the fact that we have no numbers out of bounds sort of feels nice. So that's 48, 9, 50, 51. So that's also correct. This all feels right with the 20, the 42. This goes to 20, which is 0, 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44. And then it subtracts and goes to instruction 4 again. Where else do we have? We have 2 loops in this. This is also a loop, and it goes to 34. That seems high. Why is that 34? We have it go to... This ends. This goes to the end of the loop. This should not be 32. This should be this one. So what, 12? Still looping, good. Got annoyed with websites disappearing, so now I'm playing around with archiving them. Websites disappearing. That sounds really weird. "12" is this one, and it jumps back to there. That's good. So where else do we have jumps? 0, 4, 8, 12, 16, 20, 4, 8, then back to 12. So that can jump back here, which is fine because it checks the number and then jumps to 20 if it's not 0. If it is 0, it jumps to 32. Where's 32? 0, 4, 8, 12, 16, 20, 24, 28, 32. And that's exactly after the loop, so that's also fair. This is 36, this is 40, this is 44. That then also performs a jump to the 4, which checks against the 48. 48 is this, no, what does it check against? 50. So this is 48, 40, 50. And we subtract 1 from the 48, right? From the 50, sorry. Yeah, we do that here. Subtract 1 from that one. Yeah, and then check it. Read it later. With 10,000 links. Oh my god. I thought my reading list was long. Where's it looping? Let's get the numbers back. Console.log PC. Let's see where it's running. Oh, it's just growing very big. How? This one jumps it back to 4. Did I count something wrong? 0, 4, 8, 12, 16, 20, 24, 28, 30, 30, no, 32, 36, 40, 44, 48. So it's not like we're writing to anything that is less than 48, right? All of the numbers in this region are bigger than 48. Yeah. How do we get all the way out there then? How do we get past this instruction ever? We can't jump past it unless, did I count? This is 44. 40, 36. All of these are divisible by 4, which also seems safe. This is weird. How did it get there? Let's just look at how it starts. Well, it starts out being 0, then 4, then 12, 20, 24, 28, 12 again. So we are jumping to this one. Then after it was 12 again, it was 16, then it was 32, then 36, then 40, 44, and 4. So then it goes back to this one, after which it goes through another round, where it goes 12, 36, 32, 36, 44, 48. No, not 48, 44. Are we putting something on 49? Yes. This one is wrong. What should this one be? 0 minus 53 put on 49. And 48 minus, so this is 0, 0, 53. So this should actually just be 52, right? Clearly. It terminated, and it has an 8. Good. So it works. So let's just talk about what it should do. It should be 2 to the power of 3 is what we're testing. So we can test with other numbers by saying 4 to the power of 2. Then the second to last number in this file should be 16 when we run it. And it is 16. Thank God. Yes! Good. So we actually have exponentiation now. 3 and 2. You just got to be a little bit careful with your numbers here, because if you mess up one, nothing makes any sense. That is great. Great. Okay. Yeah, so what is the next? Are there any more exercises? There is not. Okay, that's good, because I'm starting to sort of wanting to make something that can make this a little bit nicer. So compiler next. Yeah, exactly. We're going to do a small compiler now. But it's going to be just taking something that looks like this and then making the actual code like this. So let's do a, well, I mean, actually, let's just do it inside of this one so that we can take files that look like this to file2.sbnz. So the first thing we should do is just ignore these, right? That's the first thing we do. Oh, this one should be -1. So take something like this and then execute it is what I wanted to do. So the first thing we'll do up here is after the toString is replace. New regexp, no, we have the regexp. SBNZ space, no, doesn't matter. Globally with nothing. So it starts by deleting all of the SBNs. So that's good. So now we're left with this thing. We then have these brackety thingities. In here we should say if this is nan, how do we check that? How does JavaScript work? Can we say is nan to a something? Is number dot is nan to like a, or the string containing a? That's not nan. Okay, so that's okay. That's a little annoying. So what we can say is number dot is not a number, this thing. Otherwise, it is a number. If it's not a number, then we're just going to put 9999. Yeah. Yeah, that's good. What else do we need then? Does TypeScript have partition? Then you could partition in chunks of 4. What would it give me to partition in chunks of 4? Is nan 0 divided by 0? Yeah, but that's always true. I just want to detect whether this thing contains only numbers or not only numbers, which I think it's doing now. So if I write in my file here, if I run this one now, it should give the 999 on all of these locations. We can actually just console.log the program at this point and then run it with file2. Let's get rid of this one because it's going to flood us. With file2. Yeah. So it put the 999 everywhere. Yeah. Where something was not a number. Why would I want to partition them, Jens, though? What would be the benefit of that? The partitioning them in force is for human sake. The computer doesn't care. So, before we do this thing, we should add the constants. Return this thing. So if x starts with a bracket start, then we're going to treat it as a reference to a cell. Each four numbers is an instruction. Yeah, but I mean, I still don't know what difference that makes in the compiler or in the interpreter virtual machine. If it starts with a bracket, we need to allocate space for it. So we do that by We do that by doing what exactly? Actually, I think this is better as a for each now, because we're going to mutate it and do all sorts of things. So now we take the x and the I, and then we say instead down here that program on position I is actually going to be something else. And up here, we say multiple things because we need to put the constant into the program. So we say program dot length is where it's going to be. Let index. Hi Lars, welcome back to the stream. Single instruction virtual machine. That's cool. Never knew it was possible. Yeah, when I found out, I was like, this is amazing. We're definitely doing this. Dot push onto it the variable. A, I guess. No, the thing that's inside. X dot substring from 1 to x dot length minus 1. So that puts in the variable. We are gonna need, so this is now the index instead, but we're also gonna need every time we have an A to it referring to the same thing. So let's do a variables as an object that we have inside it strings, keys, which are strings, and then their locations number. So this way we can say if vars with x, if it doesn't exist, then put in the length. Otherwise, we just use this one as the index. Why is it sad? It's not assignable to string. No, I get that. Okay. Let's put it in as a string. That shouldn't matter. Else, yeah, okay, it still doesn't like it being strings. Does it compile this program correctly now? It says, how did we compile it? It's file, right? So we said 11. Yeah, I think this is the same program. So this is saying 8.123. Oh, it said 123. Okay, so that's not us. And then 4. And then 9, 10, 10. Minus 1 is its first. Oh, and that's this one. So 5 is its first variable, which makes sense because 5 is the first thing we see. Then 0, 1, and 1. It concerns me a bit that it does the 1 again here. Right, that seems bad. Why does it have 2 1s? If vars x is undefined, then do that. It still has 2 1s. Oh no, we're still, well, we're compiling still SBNZ. We're just doing it in a slightly more high-level manner, so that this file will just automatically work. Of which it really doesn't now, because it starts with a blank. We should also get rid of that. .trim. So it's 8, those numbers are fixed. 9, 10, it still has 2 1s. That's the only thing that bothers me now. If it starts with a thingy, then in this one, and we take the program length, so that way this is always assigned. push this thing where the I is replaced. If something is a variable still, then just put 999. Why does that not reuse the 1? First time it sees this one, it should put it into vars. Here. With a value. And then that means the next time it should have a value. So we're just gonna print what is in vars. Let's see, has 0, has 5, and 0 and 1. What? Why then is there an extra 1? Where does that come from? It doesn't put it in there. But we push it anyway. Sorry if everybody was screaming that. The IOTA combinator is Turing complete. Turns out there are tons of single instruction architectures, including a subset of x86. The move instruction. Is the move instruction Turing complete in itself? Don't you need any computational power? Like subtraction is what we have here. I think you needed something like that. Oh, it's not happy because they're not numbers anymore. We should make them numbers, I guess. Plus and plus, and then this is a number, but then this is a string. Ah, it's so annoying. Oops. Here, let's just convert them again like we did before. X plus x. We can't do it like that, of course, because we can't change the type once it's assigned. So this will be insters for Instagrammers. And then proc will be the Instagrammers dot mapped to numbers. Like this. So now we can execute file 2 and we get the output that looks quite different actually. Oh, because it writes something to 123, and it's -5, which we expected, right? What was the program? It was subtract 5 from whatever is in this location. So yeah, so it is -5. So this works. So we can now actually write the programs in this high-level manner. Must resist reading too much. Funny. Okay. Cool. I hoped actually there would be more stuff that it would want us to do with these references here. We're actually also not compiling the references, which I guess we should be. So that we can take this program and execute that. File 3.sbnz. This is -1. Yeah. So let's see if we can compile that. That will give us another case up here. If x that starts with the hashtag, then post it to Twitter. No, wait. Not this time. If it's with a hashtag, then we need to figure out what the index of the A is. So let index equals instructions dot index of x dot substring from 1, stripping up the hashtag, and then setting proc on I equal to index. Actually, it might be overkill in this case to have an extra variable. So can we run file 3 now? We cannot. Because cannot set property 2 of undefined, not proc, Instagrammers. And that cannot be a number because it's stubborn. Go! Finding Turing completeness is, in unlikely places, has long been a pastime of bored computer scientists. Definitely. So did it write the right thing? It wrote 5. Did we expect it to write 5? Subtract 0 from this one, so write 1, 2, 3 here, subtract 0 from 5 and write it there. Yeah, so that's good. So we can now actually just take these well, not these programs, but these ones up here and execute them directly, which is pretty cool. From the move is Turing complete paper. It's crazy why move is Turing complete. Cold tea again, as always. Delicious. I'm just gonna check something here. Whether I have some more difficult exercises with these things, or I can look them up from like an old talk 100 years ago that I did. What would that be called though? That would be called something, not all of these. Can I even find it? Is this it? Why am I'm looking in the wrong folder. That's why it's bad. And I'm definitely not gonna find it that way. Sorry guys, stay with me. Combinators, a lot of stuff, a lot of other stuff. No, do I not have it? Are there no more exercises? Definitely not that. Also definitely not that. I might not have it, that's unfortunate. Would have been fun. Yeah, I don't see it here. So I don't have any more exercise. That's unfortunate. I hope I had some cool exercises with the hashtag operator, but I can't find them anywhere. So what's up? First sentence, well known that the instruction is baroque and overcomplicated and redundantly redundant. Redundantly redundant. That's a very nice one. Figured out that you can emulate move with XOR, and you can turn a move-only program into an XOR-only one. Oh, computer scientists. Makes sense seeing as how it can be used in swapping values in temporary storage. Well, anything that can assign values, right, to other locations, you can do crazy stuff with, but I also thought they had to be able to... I don't see how move works still. Maybe that's what the problem is. I don't understand move. Let's do a git commit. Git add, no, we did the add. Commit, message initial commit, because we're done. So that seems like the appropriate time to do this. Okay, I kind of don't want to go into implementing all of these instructions and stuff because I want to do that maybe next time.